class attendance. Just often minimal.
Smiles, everyone smiles. So first in selfies, huh? I'll get back.
You're now on a 64 gigabyte memory, so we won't have problems there.
All right.
But still have extra battery. Okay. Today is the day of the permutation. And permutations turn out to have easy ways of doing just about everything we've done so far. So I highly endorse this particular type of mathematics, which, as I've said, is some of the most powerful mathematical physics that physics knows about at this time. So it's worth learning. And so we'll take a good portion of the lecture just going through some, sometimes shortcuts, because it can be fairly lengthy. I want to show a couple of ways to handle the permutational cycle notation and all of the things that make the group theory fairly elegant if you know what you're doing, including classes and the various label of pieces of the groups and other things that we're going to be using later on. And the rest of the lecture will just be devoted to the simplest applications to fairly complex things. We're going to look at how you suddenly have access to understanding and calculational ability for some molecules of fairly formidable size, including the one that I had misspelled until just a few minutes ago, the hexafluoride octahedral structures. And then one of the questions that I want to be answering as we go forward in future lectures, begin that today, understanding how level clustering that we've been studying so far in a sort of hands-off way will affect nuclear hyperfine interaction structure and basically the core of some of these symmetric molecules. This has been updated beyond what's right here now, I think, but it's getting there, and we'll be able to look at. Also, this particular page does not have what that you would be downloading has, which is a lot of links to what we talked about last lecture and what we're going to talk about this lecture. So let's get started. The idea here will be it will be helpful to have both of these screens operating, including the third one, which is showing the connection between the permutation stuff that we're doing and the groups and characters that you already know. We spend a lot of time using. So here's the deal. We'll start with a more basic viewpoint, that of someone in a pool hall, and the pool ball is being stored somewhere on a shelf. Presumably, if it's a neatnik, you put the pool balls, say all 8 of the numbered balls, in a numerical order. And then the players would put them back, presumably, but they wouldn't take time to get that ordering. They would put it down in some random way. So now it's your job, as the employee of this wonderful establishment, to put them in order. And so you have 2 hands, let's presume that, and it's natural to switch the balls 2 at a time. And this is the heart of the group theory for permutations. So you say, okay, your first job is to put the 1 ball where it belongs, and you find that the 1 ball is sitting way down here where there is now the 4 ball. So you pick up the 4 ball from the front end of the thing, and you switch it with the 1 ball which used to be at the far end here. So this is designated by we call bicycle. Just 2 numbers in there that correspond to a transposition permutation, the simplest, most basic finite symmetry group operation, called a two-flip if you like. And so bicycle is the name that we'll be using mostly. And once you've done that, you've got some work to do, and so you go look for the two ball. Well, it happens to already be in the second place, so this would be a unicycle. This would be an operation that means do nothing. This is the identity operation, or part of one. Actually, if it was a real identity operation, it'd be the whole line of 8 of these things. That would be the unit group element in a permutation setting. So I'm just indicating this one, you might pick it up and clean it a little bit, but you're going to put it back in the original second hole that it belongs. Okay? So that's up to a point what you're on the way now to fixing the order of all of them. The next one is you look for the 3 ball wherever it is, and I see the 3 ball right here, and so pick it up and put it in its spot, which is now occupied by the 8 ball, so you just switch those. Okay? So in each of these things I'm doing Dirac notation with permutation operations that I've already accumulated that are working on the original misorder of the balls, and slowly sliding them in, and here's a 3-8 going in there and making it so that I now have proper ordering up to the 3rd, up through the 3rd ball. But most of the others aren't in the place they belong, so we have to do some more. Okay, so you spot the 4th ball where the 6th ball was sitting. That means you're going to do a 4-6. That's the operation that I've tacked on here, but all these have been done now, so 4-6 takes over and does that one. 4 switch 6. Okay, that's one way to say it. Transpositions, that's all done here with transpositions. Okay, and then we got to take care of 5. 5 lands in the 5th spot where the 8 ball was sitting, and we're going to switch with it, so the 8 ball is going all the way to the very end. Well, that's kind of where it belongs. So this is a case where you did a transposition of 2 things in the right order. That's always an interesting point. Okay. Anyway, 6-7 finishes the job. I don't have to do anything more with the 8. So it's 6-7 here. After I did the 5-8, I'm done. But actually, I moved. I flipped the 8 once before. Okay. So it's this history of flipping that sometimes will be really important. And particularly, it's what's going on in quantum systems. So it's worth, getting this under control. Now, I should warn you before we go here that the permutation arithmetic is very tricky. And that's because there's so many ways to do it. Right now, we're numbering the balls. Okay? But most textbooks that I've found number the holes in which the balls go. Okay? Well, when you do that, you're actually going to be working with the inverse of the operations that we're talking about mostly here today. But you see, that's setting the stage for the Mach-Mach principle of permutations. And indeed, is setting it for the Mach-Mach principle for unitary. There are 2 unitary groups, really. The SN group, the permutation group, is a subgroup of the unitary group UN. But the UN is continuous operations where the balls are quantum mechanical spread out all over the place. The SN is assuming that they're kind of particles that we can identify and pretty well localize. If that's the case, that's the order of the day to use that. Okay, so one of the first things I want to do is really take this operation, this collection of things, and discuss it in some detail. What you notice here, apart from the unicycle, which I just put in there for the fun of it, you don't usually write it, it's a waste of time. Got 1, 2, 3, 4, 5 transpositions. So this particular permutation that cleaned up this particular day's misordered balls is an odd permutation. And this is a unique, I mean, this is something about permutation groups that is really quick to find. And it's important. The parity of a permutation is important. And this one is odd, because it's an odd number of bicycles. Okay? Flip any single thing here, it becomes even. So this permutation string here has 6 bicycles. That's even, therefore it is an even permutation. Okay? Now I'm being tricky here. I'm going ahead here and adding an extra 6, 7, so that means I had to move the original thing a little bit in order to use the same numbers. Don't let that bother you. It's just the counting here that I'm interested in, this particular venture here. And I could have moved 8 and 4 in each other and put a transposition 8, 4 out here that would undo that and get us back to what we had before. Here I did it with 6 and 7. Okay, so no big deal, but I'm just making the point now, this is an even one. Okay? And remember, well, you remember all the parity stuff that we worked with that makes that kind of bicycle important. Now the inverse of the operator that we just did, right here, okay, the inverse of this operation that ended with 6, 7, began with 1, 4, is simply then totally reversed. And the reason for that is that the bicycles are kind of neat in the sense that they have flip order symmetry. A, B equal B, A. I mean, this is basically saying A goes where B is and B has to come back and be where A is. And you'll get the same thing if you go and pick up B first and do the switch with it first and write the A as the last thing. Both of these are equal to the inverse of AB. In other words, it is its own inverse. This operation is its own inverse. We've seen operations like that, mirror reflection, right? Okay, and this is going to be generating a mirror reflection in any geometry we apply it to. But that means the minimal equation of this thing is AB squared equal 1. It's called bicycle, by it, back to 1. Okay, so the minimal equation AB squared minus 1 equals 0. So important to remember is making a projection operator pair out of these things, and the eigenvalues have to be plus and minus 1, because that's all you can get out of the equation x squared minus 1 equals 0. Okay, so these key algebraic concepts that apply here as well as they do to all the geometric operations that we've been talking about. Okay, now tricycle and quadricycle. And it takes a little bit of talking to make sure that you understand what a quadricycle or tricycle is. Let's do the next more complicated one, and that is the tricycle. Now, the first thing that I want to point out before I do this, though, is that this mess of permutations here can be sorted into a better to talk about form. And that's because 2 bicycles will commute if and only if neither A nor B equals C or D. If you have distinct numbers, different numbers from what you have here, it is guaranteed to commute, no problem. It's when there's a shared number that you got to watch out, because then it does not commute. And that's something that we want to have good ways to visualize, and we will. All of the operations that we worked with in D3, that was the first group that had elements that didn't commute. And boy, did they not commute. Most of the products that you didn't go across the diagonal. They were different on the group table. And that's going to be true of S3, which is the same as D3, as we'll see. Okay, so since 5, 8 commutes with 4, 6, I'm going to move 5, 8 up to the front here, and I'm going to move 4, 6 over here. But I can't get 4, 6 any further through that one. I can't get 1, 4 any further through that one. Okay, and I can't take 5, 8 to the other side of 3, 8, or I will be making a mistake. Okay, so now I have these numbers isolated from these numbers. And the idea is that this one here is going to make a tricycle, this one's going to make a quadricycle. So we're going to be reducing all of these collections of operations that we need to do this to just 2 operations when we get done with this. Okay, and that's why it's a good idea to take up cycles that have more than 2 wheels. Okay, it's a kind of funny. Children start with tricycles, right, and then they graduate to bicycle. Okay, we're going to go the other way. All right, it's time for a tricycle here. And we're going to consider just 5, 8, and 3, 8, what they do to a line of balls, okay? Just like the balls we have, 1 through 8. So we'll be looking at a clock. That's one of the things I want to do. Now I want to point out that 1D diagrams, some of them can be pretty confusing, and that's kind of what you find in textbooks, is some sort of one-dimensional diagram. It's usually a confusing one. Simply because the printer doesn't want to, you know, make a printing that has something that's not really in a line. It's expensive to give figures. At least it used to be. Now it's getting a lot better. But anyway, what this thing is saying is, first the 3 ball replaces the 8 ball. Okay? This is the right-hand operation. It acts first on a ket. So we're thinking of the quantum mechanical sort of Hebrew-oriented order here. So the idea is that we're going to be sort of doing our operations reading opposite to the direction that you normally do in English. But that's not really a big deal. We've been doing that already. So I have here 5, and then 3, 8 is going to do a switch of 3 and 8. That's pretty easy, okay? So we start off here with all the balls lined up inside a little ring that has a little number, blue, that tells you where the ball should be. And they're all lined up with the numbers that they belong with. But this is where the relativity of permutations exposes itself. No matter what kind of crazy way you handle permutations, and we'll show someday they're pretty crazy, that's behind the scenes. The relativity of one set of things to another, okay? And just like the Euler machine here, the ultimate Euler machine, the Mach Euler machine, I can never get a relative position like that way, okay, turning that way, or I can turn my other hand the opposite way. So permutations are going to do that too. But right now we're setting it up so we don't have to worry so much about that. But that's the deal now. So then the next step is to finish these 2 bicycles with a 5, 8. So that's just telling me wherever 5 and 8 are, I want them flipped. Okay, that's what we're going to have to do next. And that's what happens when you do that. Okay? So after I've done this one, which takes the 5 and the 8 and switches them, okay, they used to be here and here for the 8, now it's the opposite, and we're done. That is a tricycle, but you kind of have to draw it in a circle like this to really see it. This is a mess. Okay, that's the trouble you get with this kind of 1D diagram. All right? And we're going to do a quadricycle next. That looks like a bicycle wreck, is what it is. Okay, so basically what we're saying here is this thing means 3 goes to 8, goes to 5, goes to 3. 3 goes to 8, 8 goes to 5, and then 5 goes to 3. That's the way you read a tricycle. It isn't just 3 goes to 8, 8 goes to 3, like we had here. It's got the extra thing to it. And furthermore, and this is really important for counting these things, and that is that this particular tricycle can be written 3 different ways that are equal to each other. I simply slide it along, the 3 to the middle, the 8 goes down to the end, and the 5 pops up and comes back to the front. So if we had a circular notation for these things, that wouldn't be a problem. You just have 3, 8, and 5 around a circle, something like that. That turns out not to be necessary. We get to figure out how to use these things without having that extra visual aid. But nevertheless, it is important to have this because that's what the cycle is here. You see, 3 goes to 8, goes to 5, goes to 3. Okay, that's this one. But 5 goes to 3 goes to 8 goes to 5 is another way to say it, and so forth. You just read it. Who do you start reading it with is immaterial to the actual operation. We're assuming that. Now, of course, not true. Quantum mechanically, you can start moving it. I mean, the real physics of doing this with some sort of wave packet is not trivial. We're going to try to make it more palatable, but not it. So, these statement that I just made here, 3 goes to 5, goes to 8, goes to 3. Another way to say it, same thing. Okay. Now, other thing that should be noted, I guess, is that the rest of the operation that we do with these pool balls, which we'll do right now, is going to give us a quadricycle. And that's because there's 3 of these entangled permutations here. I don't know if it's proper to use the word entangled, but I'm going to do it anyway. Okay? So we got to do 1, 4 first, and then 4, 6, and then the 6 in this, is shared by these 2, so we got to do that guy last. And it's always the one on the right that starts the thing. So that's what we're doing. So we're going to consider 3 bicycles, and start off with the thing all in order here, and we're going to do the permutation that goes with the tricycle. So the first thing is to flip the 1 and the 4. There they are. They're the ones that are out, only 2 that are out of order right now. And then we're going to flip the 6 and the 7. Okay? That's going to happen in just a minute here, but we do the 4, 6 first. That gives this, after having done the 1, 4. Okay? And then finally, we flip the 7 and the 6. Now it kind of looks like we got a mess here. We got 3 lines sort of pointing off different directions, but the way to say how this happened is with a quadricycle. So this is going to be a 1 goes to 4, goes to 6, goes to 7, goes to 1. That's the quadricycle that's going to pop up here. Okay? So we're going to apply a quadricycle that takes you around a circuit that has 4 sides. 1 to 4, 4 to 6, 6 to 7. That's the last one. But you don't forget the 7 back to 1. This always goes back to the beginning when it comes to the parentheses on the right. Okay, so that's cycles, right? Does it make sense? Okay, it's the kind of stuff we're going to be using a lot of. Now the point is also that there's 3 bicycles here. So the quadricycle with an even number of numbers is an odd permutation. And the tricycle with an odd number of numbers is an even permutation. 2 bicycles, that's the number you look at. It's even. This one, got 3 bicycles, that's odd. So it's that simple. So the bicycles are always hiding in the background for all of these more complicated operations that we're going to be doing. And they determine parity. All right. So good. And here is showing the 2 overlapping. Okay. And you can see even this diagram starts to get to be a mess if you have too many of these cycles in there. So we need a better way to do this. Now, the key to that is a little figure that I put in the early textbook, that Quantum Theory Computer Age, at the end of the first unit. This is sort of a shot where I describe what I just described to you in a not as good a way. Basically what we're doing here is unraveling the permutation that we just faced. That is, here are the balls unordered, and here's the pockets that they're supposed to go in. So what I'm doing here, and this is kind of zigzag thing that you do, you say, okay, I'm going to grab the 1 ball. It's sitting in the 7 right now. So let me go and see what's in the 7. Where is the 7 ball that should be in that place right there. So I'm just sort of looking at what I might be doing, and I'm just doing it real quick. I'm doing a sketch of what I'm going to need to do. Okay? And once I've got the 7, I look, oh, it's in the 6, so let me draw an arrow to the 6. Now I look where the 6 is. It's in the 4. That's way the heck up here. Let's draw an arrow to the 4. Zigzag, 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 you see. As I go through all of the balls that I can with that, and I end with a quadricycle. Because the last step here is 4 is at 1, okay? And that's right above where we started, okay? Right there. So, this closes. This is the way you close. Somehow you find a zigzag procedure to close a permutation, a complicated, say, quadricycle or a billion cycle. I mean, that's what quantum mechanics is going to give you eventually. And you've got to find a way to note that, okay? And again, this is written 4 different ways. So, fine, that's good. Now, there is a fly in this ointment right here, this particular method right here. Next higher number that doesn't exist in that quadricycle, so it's 2. I go for 2. Well, big deal. 2's already home, so nothing is, move on, nothing to see here. Okay, but the 3's part of a tricycle. I'm sorry, yes, a tricycle, 3, 5, 8. Okay, now, this is okay. This is unraveling this thing, but what we got was the inverse of the pool ball operation. Okay, so this just watch out when you do something with a permutation. Make sure it's what you want. Okay, now product arrays are probably the safest way that I know of to make sure you don't perform an error, but they're not foolproof. They're just as foolproof, nearly foolproof. Okay, nearly foolproof. You can always look at the wrong thing and use that number instead of what you should be looking at in a given operation that we do. Okay, so here we start off with the very first permutation that was necessary to start our pool ball reordering. Okay, and that's 1, 4. Okay, so you have the pockets, either numbering the pockets or numbering the balls. You've got some kind of ordering here, and at this point you switch it. 1, 4. Okay, so now the 4's here and the 1's here. Everything else is still in order. Okay, so what we're going to do eventually is get that thing right there. Okay, 3, 8. All right, same deal. Keep the ordering you had. Only look at the numbers on the balls. Okay, switch them. Same deal here as I pull off the 4, 6. Okay, those two switched. So you see, this is very clear. It's very clear what you did and what you get. Okay, we're almost done here. I'll do 2 at once here. The 5, 8, that's this, and the 6, 7. Now, what do you got here? Okay, what is it that has happened to this thing after all of these? Okay, they're not really in the right order, so that's not what this does. But you can make it so it's in the right order. You go ahead and write the numbers that they originally were located, and then we'll say a few things about that. Okay, so what you do after you've got these things here like this is you now sort them into by tricycles, quadricycles, higher order cycles. Okay, so I see here that 1, and this is a zigzag now, that will really work. Okay, 1 over 4, well, where the heck is 4? There it is. Okay, well, that means the next number that's going to go here is 6, you see, but we're not done yet. The 6 is sitting over here 7. It's not one of the numbers we've seen already, so that means that I got to put in a 7 right there. Okay, and now maybe I might have to put all the rest of the numbers after this thing. Let's check to see where the 7 is. Oh my gosh, it's over the 1. So you're done with this cycle. Okay, you're done with this cycle. There's still some guys we haven't used yet, right? Well, there's 2. He never goes anywhere, but we do have 3 more numbers sitting here waiting, and they're the ones that made our original tricycle. Okay? But this little pair of numbers here tells which new number, and it's sitting over an old number. So it tells which new number now sits in the space that started with the old number. And that's important. That's, you know, thinking about that is solid. Doing other ways, well, you better get them so they have the solidity of this. Okay? And we went ahead and did the tricycle here. It was already there, just a matter of outlining it. Okay? So it's a cycle and can be read 3 different ways. This is a quadricycle and can be read 4 different ways, but the graph doesn't change. It's kind of invariant. Okay? Now, shortcuts. This is kind of neat. But this takes a little practice. Instead of drawing this whole chart, I just go, last op, move 6 to 7. That's the last thing that happens is 6 gets dropped where the 7 was. But you got to know where the 7 was. Whence came the 7? So you got to go back and look at this thing. It first said 6 to 7, right? But then you got to go back and say, hey, 7, where did you go? Well, you went to 6. And then there's another 6 down here that acted even earlier. Remember, the order of this thing is this first and that's last. So we're undoing the history here. Okay, 7 goes to 6 and 6 goes to 4. But we're not done yet. There's a 4 down here, right here. Okay, and it goes to 1. So I know for sure that 7 is going to have a 1 after it. Okay? When I actually write the permutation for this thing. So this implies a 6, 7. This implies a 6, 7, 1. So it depends on whether you want to write it on this side or on this side. It's a little dangerous to write on this side because we're going to have a bunch of numbers going on. Some of them might go in and cut you off. So to make this a shortcut work, you've got to clear some space and know where you're going and decide, you know, from practice which works the best. Okay? So you keep asking where things go each time, and finally the last thing that you get here is asking about the the 4, and that will finish this. This will, you started with 6, okay? It says go back to 6. That means you've finished the cycle, and you write that down. So these are just some examples of doing some calculations, reducing various things. Now, an interesting one, I think, is this one. 1, 2, 1, 3, 1, 4, 1, 5. It's very entangled with 1, but it's really easy to see why that comes out to be 1, 2, 3, 4, 5 cycle. Okay? So you learn all kinds of things about permutations using the shortcut as well as the long cut. This thing down here is getting, let's see if I'm doing that right, 1, 2, 3, 13, 14. This one actually is doing our pool ball permutations, but with numbers slightly different. Anyway, that is some, you know, these are things, I could go on about this in some detail, but this is something you need to practice if you're going to, you know, play with permutations. And figure out how you program it, right? Because obviously we're going to be dealing with S60. Pretty hard to do S60 on paper. It's got 60 factorial elements. Right? These are big groups. Monster groups. Okay? Bigfoots. All right. Now, the algebra, class transformation algebra, that sort of stuff, also how the cycle labeling really works, and relating it to various things. What I want to show you is how simple it is to do a similarity transform. That is, to do this particular combination of permutation, namely a bicycle, and then followed here, I should say that the bicycle follows a 1, 2, 3, 4, 5, 6, 7 cycle, okay? And on the other side, I put, this whole thing is called T. On the other side, I put the inverse of that, which is, well, I didn't need to do that, because we know 1, 5, and 5, 1 are the same, but go ahead and do it. And I'm also, since they commute, leaving it on the same side. Normally, if this thing had numbers entangled with that one, you'd have to put it over here. But mainly I have to turn this one around and read it backwards. So I go 2, 6, 9, 4, 8, 3, 7, 2. Okay, 3, 7, 2. Do you catch me doing that, right? So there is a similarity transformation. And then here's the shortcut, so-called, method for doing it. I think it is probably a little bit shorter than this. And it's probably a good idea when you're just really worried about the results that you're getting, that you go ahead and do both of them. And if they come out right, it's a good chance you've done the permutation correctly. Okay? But I just wanted to show you what happens from a similarity transformation. And you can see that to do a similarity transformation is actually very easy. There's a shortcut to that. But let's just go ahead and make sure we understand what's going on here. Okay? We're all working on the thing that's the last thing that happens, and that is 1 goes to 5, okay? And then the question is what happens next? Okay, what we're doing here is looking carefully at the operation, and we're including this thing in there. Okay, so there's a 5 entangled with this, so I've got to keep going down the line here, finding other numbers. And so this whole thing is sitting right here, and this is the shortcut to get the thing reduced to cycles of some kind. Okay? So, we started with something that had a quadricycle and tricycle and a bicycle. Will we end with something that also has that? And the answer is has to be yes, because cycles determine classes in this business. So anyway, what I do is I go, okay, first thing that's going to happen is 1 went to where 5 was. Well, where the heck was 5? Well, this operation already has taken the 5 to 6. Okay, am I done now? But no, somebody took the 6 and put it in a 9. Why would you do a thing like that? Well, that's the very first permutation that happened. So right now I know the operation that I'm going to get from this chain here is going to have a 1 and a 9. So the question is then, okay, 1 goes to 9, but where was that 9 really? Okay, it's been knocked around by all of these permutations, including that one, but we really need to worry about everything that happened to 9. Okay, so we go back and look, and 9 goes to 6. Okay, and then 6, we look for the 6. 6 goes to 7 by that one, so we're already in the 7th slot. And then is there any other place that we have to look? Well, yes, 7 is down here going to 2. So I know that's the next number in the cycle. Okay, 192. And we just keep doing that. Okay, next stop, all right, is to look at where the 2 really is. Okay, and the 2 here, I don't just pick the 2 that I was looking at here, because that'd be down here. I'm looking at the original 2. The last thing we saw in this operation was the 2 went to the 7. But where's the 7? Okay, this 2 says 2 to the 7. Oh, that 7 got moved to 8, didn't you hear? By the middle permutation. Okay, well, fine. But where the heck is 8? Did 8 get moved? Yes, it did. 8 got moved to 3. Okay, so that means I tack another 3 onto this one. Okay, well, fine. Now we got to start all over again with the 3 up at this end. 3 goes to 8. Okay, and then 8 right here goes to 5. And then 5, it's got to be somewhere. Oh, 5 goes to 1. Oh boy, we're done. That's the other side of the cycle. So I put a parentheses on it. I don't write it. It's already here. Is that clear? Well, it's something you got to do practice to get thing. You got to learn. You got to read to the right. You got to look at the numbers that are coming up rather than ones you might have already seen. Never go backwards. Lots of things to screw you up on that. Now, as I say, to check it with the array method is imperative. Okay, So when we get done, we would hope that we would have it. And that's a question of, whether, what sort of cycle is waiting at the bottom of that thing. And indeed, it is the desired result that we got. Now remember, we don't stop this thing. Whatever numbers I've missed after I close it, I've got to then take, say, 4 next, and that one closes very quickly. 4 goes to 5 and 5 goes to 4, so that's an easy one. And this one isn't very hard either. It turns out to be a tricycle. So it's those 3 operations, quadricycle, bicycle, and tricycle, that we started with. That's this guy, 5, 6, 7, 8, 1, 9, 2, 3, 4, and we end up with these 3 things right here. This guy, quadricycle, this guy, 4, and this. So I just stacked them on top of each other. The 1923 sits right here underneath the 5, 6, 7, 8 that we started. So there's a quadricycle going into a quadricycle. And then there's this 5, 4 that we pick up in the middle here. It's now being drawn underneath the original 1, 9, and the tricycle the same way. Okay, so there is a coordinate transformation in permutation theory. All it does is renumber it. It does not change the cycle structure. But more than that, if you look at this thing, this transformation, 1 goes to 5, okay, and 5 goes to 1, okay? There's a 1, 5, and there's a 5, 1 right there. That's this thing. Okay, so there's your bicycle. We could have done this without all of this. I just use the transformation, read it off, and I'll make 1923. You see, there's the 9 goes to 6. Okay, there's 9 goes to 6 right there. All right. There's a 6 involving 2. There's the 6 involving 2, and so forth. Each one of these numbers and its neighbor is reflected in the up and down between the original numbers that were in the thing and the other class element, the Similarity Transform guy that we got from doing all of this. You can just read it off from here. Okay, that's an interesting thing to see, right? All of the analogs with the geometrical kind of transformations that we've done start to make their appearance in a quite beautiful way. Now, I haven't been keeping up on this screen, so I'm going to go ahead and do that now because we're going to have lots of physical things to worry about here that come up. But the next deal here is where most permutation group discussions in textbooks starts. They just don't want to do the dirty work that we've covered right here. But this is class labeling and counting and all of the tableau stuff that comes out of that. We're going to start to infringe on that area very shortly here. But the basic idea is that permutations are classified by the numbers of unicycles, say nu1 unicycles, nu2 bicycles, nu3 tricycles, etc. And the idea is that the cycle reduction is designed specifically to put different numbers, distinct numbers, in each of the cycles that you get. So there are a couple of things that happen. First of all, those cycles commute. You can do them any order you want. But the cycle length has to be the number of balls that you've decided to consider. Now this is where the quantum mechanics gets weird, because you say, how far do I have to go in this sum? How many particles or wavelets or whatever, magnons, you name it, how many am I really going to have to worry about? So that's the choice that you're going to make, because, well, if you've got to do the whole universe, you've got a big number there. If you're going to just do 2 sets of magnons, you've got a big number there. Okay, so this can get really hairy. But the idea is that whatever each permutation has in terms of the numbers of these various kinds of cycles, then 1 times the first, 2 times the second, plus 3 times the third, and so on, n times the nth, that has to add up to the number n. Now a good example of one that we'll be seeing very shortly here is for S4, which by the way is a tetrahedral group. It's also the octahedral group. And here's a typical tricycle, which has one extra number, a singlet. So you got nu 1 equal to 1. There are no bicycles in that particular operation, but there is one tricycle. So you can see that as you start to go up in size of cycles, you start using up numbers pretty quickly. S14, for example. And here's the other thing that's really annoying. And that is, we only got 10 fingers. If you're doing hexadecimal, you see, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F, right? You get out to 16, you have a 16 fingers, right? So how do you do all this cycle stuff when you have to write 2 digits? You got a problem, right? So when you start working with permutation groups past the 9, you gotta think of some, you know, you gotta put commas in, right? The bicycle has to have a comma, which is an extra thing to write. It is an annoying piece of this, right? So I recommend sometimes do use hexadecimal. There's no, you know, nothing wrong with that. Okay, so right now I'm going to start this in 14, 13, 12, 11, 10. I've got 5 unicycles, so that's nu 1 equal 5. Then the bicycles, 1, 2, 3 of those. And I just have enough room before I go into negative numbers to put here a whole tricycle. Now if you want to have 0 be part of your permutation, good. That makes you have 10 real fingers. But I'm stopping here. I just have a tricycle, nu 3 equal 1. Okay? That's just one of many classes in S14. This is one of the 5 classes in tetrahedral and octahedral and S4, which are all the same group in an isomorphic setting. Okay. So for n equal 2, there are just 2 classes. That's fine. You can have a bicycle, but you of course have the identity. So that's kind of trivial, but remember, it's always there. Every permutation group's got one of those as a subgroup. And the next stop is the 6 permutations that live in S3. Okay, and there are 3 classes of S3. Remember D3? And those classes are labeled by partition structure. 3, 1 plus 1 plus 1. So if I'm putting the plus signs vertically, that would be an anti-symmetric if it were the tableau, which we're going to discuss. But right here, it's just a cycle that has three unicycles. It's identity operation. And then there's a number of these. 1, 2, 3 left alone. 1, 3, 2 left alone. 2, 3. So 3 bicycles live in the permutation group S3. Okay, and those are the 120-degree rotations. When we, as we'll see. And finally, this partition right here, which is just a plain tricycle. Okay, that, and I misspoke myself. Yeah. This one is the 120. These are the 180 degrees, or the reflection plane, obviously, because they're bicycles. Okay? All right, so that's something I want to look at first, as these guys that have very simple structure, but I need to, count. I've got to be able to count how many of these classes we have in general. It's really easy to count when we talk about the small numbers. The big numbers, wow. That's a whole different ball game, which I'm going to try to explain right now. And this is kind of squirrely, this description here, but it's based on Lagrange's theorems that we worked on when we first did D3. And what we have here is a bunch of cycles, and let's just pick out a particular M cycle. It goes 1, 2, 3, 3 to M, okay? And what you notice about an M cycle is it can be written M different ways. We saw the tri and the quadricycles being written 3 and 4 different ways that were all equivalent, all equal. So you're just pushing the ordering of 1, 2, 3 to M around the cycle. And of course, 1, 2, 3 is the same as 3, 1, 2 is the same as 2, 3, 1 in this notation. Okay? So you got to remember that the numbering of these cycle structure, it has a redundancy. That is, it has a whole bunch of things that aren't different operations. And if there are new M of these in your particular permutation, God forbid, because it's a large thing, you've got a really big permutation you're worried about, you have M to the number, power, such reorderings possible. So if I got 4 or 5 of these, I've got 4 or 5th power of the 3 different ways that I can write each one of them. So you see that the redundancy just is really getting to be pretty big for these cycle structures, particularly the larger ones. Okay? And each of these cycles contain distinct numbers, so they mutually commute. That is, there are new M factorial. Now that really goes up. That's super redundancy, okay? With just 2 big deal, okay? I can commute those, yeah. But if I got 3 of them, I get 6 ways to commute. 3 factorial, then 4 factorial, 5 factorial. Factorial goes up very fast. So those are the numbers that we need to divide out, the product of the factorial and the power of the M for each type of bicycle, then the tricycle, then the quadricycle. If n equals 4, you're done, but if n is equal to 5, you've got one more factor down here that's even potentially bigger. So you see, things start to get pretty big and complicated fairly quickly. But so far, we've had only to really look at the details for octahedral symmetry. That's the most complicated symmetry that we've really dealt with so far. And you remember it had 5 classes. I want to show you what those classes look like with the octahedron. Okay, now how can I do this for the octahedron? It's got 8 things, right? Well, yes, it does, but you can divide up the 8 things in 2 halves that are sort of tetrahedrally oriented. And the permutations of those 4 numbers map perfectly onto the 4 factorial. That's 24 rotation operators for the group O, or octahedral. But if that sort of bothers your head, if it feels, oh my God, I'm never going to be able to visualize permutations that are written on octahedron, get me out of here, I point out to you this guy right here. And that's a tetrahedron, which is isomorphic in its symmetry to the O. So the tetrahedron turns out to be the winner here if you really want to get in to the permutations and their effect on nuclei in molecules. And so that's the one that we would look at. But whatever you look at, here are the 5 classes. All unicycle has the identity class, only one element in that thing. But then right away you get a pretty big class here. And you see when you go ahead and use this formula here with 4 factorial in the numerator, that's n factorial, and then these products of the new and then the order to the nth power, say for bicycle, is new number of bicycles factorial times 2 to that number power, you see. And if nu is 0 anywhere, 0 factorial is 1, not 0, don't forget that. And then 3 to the 0th power is also 1. So most of these numbers turn out to be 1, and you only have to get a few numbers in most of the calculations that you do, the molecules that we've considered, including buckyball, the monster, is taken down easily by this kind of reasoning here. So here are the new numbers. There's 4 unicycles here. Here's 1 unicycle and 1 tricycle. Okay. Here's 2 bicycles. See them? And then a quadricycle. We've got one of those, and then we've got a whole bunch of bicycles, and the number of them is 6. And then there's 6 of these guys. These are the 90-degree rotations, and there were 6 of those. And then these were the 180-degree rotations, X, Y, and Z. These are 180 around the diagonals. And then this guy's that wonderful trigonal guy that the group has, and there are 8 of those. Those are the actual rotations around the face of octahedrons. So the numbering there actually makes a lot of sense. Okay, so good? Well, here's the list of them. Okay? There's all 8 of the operations. They're all unicycles followed by tricycle. But put them on any order, because there are different numbers here than there are here. And all of these things that we set up by cycle production. And then same thing here, they say. So these commute. That thing is just all by itself, the quadricycle. There's the quadricycle that defines 90-degree rotations. And then here, that is, it does it for the octahedron. From here, it's a rotation inversion. Okay, ready to rock? This is the basic ideas of the permutation stuff right here. And just getting into what's going to be the irreducible representational analysis of these. Okay, so let's see if we have anything here. This is where it really starts, just with 2. And the deal is that you also label the projectors and the irreducible representations by partitions. 1 stacked over 2, that's one way to write it. I would probably turn the thing on the side and say that's 2, this is 1, 1, but that's half a dozen of one, 6 of the other. Okay? And anyway, what we're looking at is our very simplest group, C2, or CI, or CV, or CH, all of the different names they give to various kinds of groups of order 2 that are at the bottom of every crystal point group, and then every molecular point group after that. So A1 and A2 is the usual names for a horizontal tableau that's symmetric and a vertical tableau designating anti-symmetry. And if that were all with 2, we wouldn't have a course. But we got a lot of empty space here to fill. Okay? And you see it on the 3rd board there. It's really quite an amazing bunch of stuff that the permutation calculus, the tableau calculus, the calculus of these little boxes here, just numbering them is an amazing thing. The idea that I can actually characterize and see right away that the E representation for S3, which is called the E representations for C3V or D3. This is C3V with reflections here. Put 90-degree rotations here, leave everything the same, and that's the dihedral group D3. Isomorphic to this, and isomorphic to this powerful mathematics of the tableaus and the cycles. So basically, we've got a 3-cycle here. You maybe call that a 3-cycle, most symmetric representation. Then there's the most anti-symmetric representation. That's this one. Okay, all 3 of these bicycles get a minus eigenvalue from that one, whereas they're definitely plus. And it doesn't matter whether you're talking about a tricycle, which is an even operation. Remember, the number of numbers in a cycle, if it is odd, like this one, that means the permutation is even because it's two bicycles to make a tricycle. And keep that in mind. And then finally, this guy right down here. We're going to be able to get the characters, the dimension, you name it, for any of the permutation groups. And you remember, it was a bit of a struggle to get this character table, right? Those days are over. Said the carnival barker as he tried to sell Father John's cough syrup. Right?
Burnside's algorithm.
What's that?
As he tried to sell Burnside's algorithm.
Oh, that probably wouldn't go over with the crowd. Yeah, we'll talk about Burnside later on. Anyway, you can see that this is incredibly powerful, and you can see the correlation between the tableaus in, say, S3, and here we're talking about S4, and I just go ahead and draw the tetrahedron because it has 4 numbers that are getting permuted in these cycles right here, respectively. So this is what we used to call those operations, the sigmas on the diagonals, the rows, the rotations on the X, Y, and Z, and then the big R rotations of 90 degrees around each of the faces of a cube, or the points of an octahedron. And then the tetrahedron has the same deal. It's just that with the tetrahedron, this has got an inversion on it. This is an inversion 90-degree rotation. This is an inversion sigma, which as you know is a reflection. This one is the queer one. This is really queer. People aren't used to doing some rotation other than 180 and then doing an inversion. That is hard to visualize. Well, if you don't have a cube like that. That's something you can always do there. But that is the only one in this collection that is hard to visualize. The others are the same for the octahedron. This is the T group right here. And those are all 120-degree rotations around respective points. And obviously the points are 1, 2, 3, and 4 for tetrahedron. They're faces for the octahedron. But they are the corners of a cube. So 2 tetrahedrons fit to make a cube. And keeping all that in mind gives you something in addition to the richness and power of this stuff here. And the idea that this collection of 3 things right here, which are tableaus, and the rule on the tableaus is that numbers have to increase as you go to the right and as you go down. Okay. So the numbers here, 1, 2, 3, and 4, you can only use one of each to number the tableau. You just find out how many ways you can put 1, 2, 3, and 4 in that. You don't need the formulas that we're going to reveal here. But here I go 1, 2, that's okay. Here I go 3, 4, here I go 1, 3, here I go 2, 4. That's a legitimate ordering. And then I just go ahead and switch it. I put the 1, 2 here and the 3, 4 here. That's all I can do. Any other way I arrange those numbers, I do not get a legal tableau. So those 2 count for this character, the dimension of the E representation. And then these guys, obviously, that's just the only thing I can have. It's all lined up, it has to increase. This one, same way as I go down. So it's clear, there's only one each of those. Those are A1 and A2 that we've used as our pseudoscalars and scalar. This is a pseudo, that's the real scalar. And then there's E, and then there's these 2 three-dimensional representations. Okay? Now, what you can see by my coloring, I've colored the 4 to be gray, and just imagine it isn't there. If it were to disappear because the symmetry was broken in the axis that involves the 4th state here, say this 4 here, and then I've got 1, 2, 3 left as a symmetry, a trigonal symmetry, that is this symmetry, then I know that this triplet is going to split into a singlet that is the one called A1 up here, and a doublet that is called the E up here, you see? So your correlation job between this group and that group is trivial once you get used to the tableaus. Okay? And then here's T1, that's the vector XYZ. This is the tensor one, so it's a bigger guy, so it lays down on its side and it's more symmetric. The vector is less symmetric and more anti-symmetric than the tensor second rank. And you have a feeling for that already by looking at the wave functions in our top-down approach, right? So this guy here is X, Y, and Z in a coordinate system that is commensurate with this tetrahedron. I think I call that U, V, and W, and we'll come back to that later on. Now that's something we won't be doing, obviously, today, is to look at the actual matrices that go with these. A 3x3 matrix, another 3x3 matrix, and then a 2x2 matrix, and of course these we do have. They're just numbers. We're going to be able to do a heck of a lot just with characters. But I'll mention the fact that all of that can be calculated, because this is kind of the last step, next to last step, before you really step off into the very great unknown. We still have S5 to look at, because that's going to be involved in this thing. Okay? And then it turns out that if we're going to play with an octahedron, we've got an S6 that we've got to look at. And that's where it really gets squirrely, and we'll try to explain some of that here. In any case, here is something that you might assign to S4, namely a molecule, and there aren't all that many square molecules, but if you've got one, it's going to be an S4 symmetry that is much bigger. S4's got 24 elements, just like the tetrahedron. It's going to be much bigger, and I used a greater than sign there because you can't really say that this thing contains that one. It doesn't, but it's not directly anyway. The D4 or C4 that are in there are not something that you immediately get using a permutation analysis like you do.
Bill, can I interrupt
yes.
you real quick?
Yeah.
Have you ever thought of the possibility that these symmetry groups describe the transformation properties of hidden pathways on Riemann surfaces?
If I was better at topology, I probably would have a good answer for you, but you're going to be the one to discover that.
Maybe.
And that is very important. I mean, taking all of these crazy symmetries and embedding them in curved spaces is
Complex space, too. Because I'm thinking about the rotational energy surface right now, and
looks like
it could even be S4.
Yeah.
Right?
Oh, absolutely.
And you see the
definitely.
solving over the reals, you can see these disconnected cycle contours,
Mm-hmm.
and there's going to be abelian motion along any one of those contours.
Yeah, if you stick to something that's one-dimensional, even if it's curved,
Right.
the waves are just going to march on that.
And it's possible to linearize it too, but
Right.
with appropriate coordinates. But then what we haven't seen so far, which may actually be out there, is that there are hidden solutions of the Hamiltonian constraint over the complex numbers,
That'd be
which
great if we
provide
could.
backdoor pathways
Yeah.
for the wave function to tunnel between those
Mhm.
paths. And so if you look at this,
Absolutely.
probably
Moian.
Riemann surface this has a genus probably higher than one.
Mm-hmm.
It's going to have some sort of, it could actually also have a finite, and probably would have a finite symmetry group describing pathways between those contours that we can't usually see.
A little group that'll be finite?
Yes.
See, yeah, I'm not going to stand here and say, oh, no, that's impossible. It's
No,
clearly something to look for.
Yeah,
And I
it's
have
actually going to lead to antagonism, though, because you know you've already done the calculations, and they worked fine, where the tunneling integrals that go between the curves actually go through real
I
space.
was always suspicious of that.
Yes, they go
And
through.
Heller works with imaginary time when he does his tunneling.
Oh, he does.
Yeah, so, and that makes sense.
Yeah.
You know, it turns it into an integral over an exponential, big deal. But, and it's not, you know, it's also suspicious.
Yeah.
It's just as suspicious as what we were doing when we started with the asymmetric top. And
Oh.
got, you know, you got good answers.
Yeah.
You know, like 3 figures, okay, that's not good enough. You know, when you're doing spectroscopy, you need more than that. But, yeah, well, we hope, we can very much hope that you keep up your work, because that is where things should be heading. Okay, now the tetrahedral guy, this guy, just to remind you, we have already said, it's a table down there that I want to look at, this thing. This is the O3 correlation, just so you know what we're talking about in a few minutes here. It's not very different from the correlation that we looked at between the O3 to the octahedron, and we almost use the same notation, but if you want to be kosher with the crowd, your T1 and T2 become F1 and F2. Not a big difference, but you have to watch out, and then you get systems 0 plus, 2 plus, and you get 0 minus and 2 minus equally for a tetrahedron. It is sitting there trying to make its parity, which it doesn't have right. So it wants to have this arrangement plus the inversion of that arrangement with a plus sign sometimes, that's in phase, or minus sign other times, which is out of phase. So that's what the little plus and minus, that is so important for designating parity of the entire molecule, the core of the entire molecule. And once again, the operations that we're talking about here, 2 pi over 3, 120 degrees, 8 of those guys behind this class, and then 3 behind that class. And these are the permutations that we're developing now. And these are the old-fashioned notation for those permutations that you used before you could print boxes. And now that math type has been sold to Barcelona, Spain, I'm not sure that we're going to still be able to do boxes, but I am hopeful. I talked to the people yesterday. So they're still going to have their San Diego office, but all their money's going to go to Spain. Did you know this?
I didn't know this.
For me, it's kind of a disaster, but I think it'll work out. At least the fellow I talked to was actually happy about the thing. They all got raises. We've heard that before, haven't we? Just before it closes.
Now, they used to have a component of that embedded in Microsoft Word, right? For doing the equations.
It's called Equation Editor, and it was designed by Design Science.
Do they still have that relationship with them?
I haven't asked about that one. I'm having enough trouble with the Apple relation.
Radio.
Yeah, so I haven't
Yeah.
checked out what the Microsoft business is. Anyway, let's go here because I would like to very quickly show, once again, we did it a little bit in the previous lecture, these absolutely magic formulas that give you what we're going to be talking about in the next lectures. And that is a formula, or a pair of formulas, that give us, first of all, the irreducible representation dimensions that you have for permutations. Sn, this is for Sn here, we're getting an entire really simple formula for all of the dimensions, like if we want to find out what T2, that's this particular tableau, or E, remember, this particular tableau is, and it is for S4, so I always put a 4 factorial in the numerator, and then I divide by the tableau filled with hook length numbers. These hook length numbers here are the key to that. Now let me leave on the other slide this old-fashioned drawing, and I'll put up a more recent drawing where they're drawn one over the other instead of side to side. So here's the hook length product for an imaginary tableau of S8, okay? And remember, S8 with 8 factorial, that's a lot of elements. That's a heck of a lot of elements, right? Not anything you'd ever do on paper, unless you have a powerful thing like this. There's no problem figuring out what it would be. And I would, in this particular case, stop at 8. This would be 8 factorial up there, but it would be 8, 7, 6, 5, 4, 3, 1, which would cancel most of these numbers and give me a small number, which is what I'm looking for. But here are more examples of S3 cases, the A1, A2 case. Better work, right? That's trivial. 3, 2, 1 over 3, 2, 1. Yeah, sure. No problem there. It's the fact that you get these guys right. And then you get more as you go to S4 and so forth. And of course, S5, we're going to need it for that. And it turns out for this molecule, it's got 6 nuclei that are flying. So we're going to need S6 for that one. That I just want to sketch very roughly today, how that becomes a reality. But anyway, we also have to deal with what's called the intertwining symmetry by people that have love to use big words, big fancy words, sort of when we talk about the entanglement in information theory, right? Which used to be called correlation. Okay, but correlation, oh, big deal, right? Entanglement, oh, that's so sexy, right? Well, it's also so sexy you don't ever stop and look and see what it is. And that's true for this thing right here, where we're talking about the basic idea of the intertwining of a unitary group of transformations like U2, the actual spin rotations, say, but if it's in momentum 1, it's going to be vector rotations and so forth. That set of continuous operation, the continuous Lie group, okay, gets its basic properties defined by what it intertwines with, which will be one of the permutations depending on what representation you're interested in. So that's stuff we're going to talk about in the next few lectures after this one. But you need to know the dimension of the tableaus that describe both of them. And they'll often be the same tableau or a tableau that is the flip, that's what fermions do, of the one that you're working with for the spin operations and the one you're working with for the permutation of the orbiting particles that make up the molecule or whatever physical object you happen to be working with. So this is really powerful. Now instead of putting n factorial up here, if it's the unitary guy you want, it's going to be an m-dimensional thing. You write the m's down the diagonal of the tableau, just without factorialing them at all. You just write m, 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 m. And then you put m plus 1 above, and then m2 plus 2 above that, and below, guess what it would be? M minus 1, m minus 2, and m minus 3. You put those numbers in for whatever m you want to have. Say you're interested in Gelman's U3 group, okay? That's a famous group, the eightfold way, right? Do you remember that? That's, I think he liked to, you refer to things in esoteric literature like James Joyce, the quarks. 3 quarks for Mr. Mark. right? And that's where you got the name quarks. Meanwhile, George Zei just called them aces. Everybody knows what aces are. Usually there's 4 aces unless you're cheating, right? In this case, there were 3. He thought it was funny. But anyway, here I look at the 3 on the diagonal. There's only 1 box on the diagonal, so that's it. Then I go 4 here, and I go 2 there. Then I divide by the hook lengths. Bingo, 8. That's the dimension of the regular representation, the reducible regular representation in a Lie algebra of U3. And then this one is the one that won the Nobel Prize. This is a symmetric arrangement. Call it the A1 representation of SU3. Okay, you go 3, 4, 5, divided by hook length 3, 2, 1, 10. That's called the decaplet in high energy physics. And the decaplet only had 9 resonances that people could identify. And Gilman said, hey, there's a 10th. And sure enough, they just looked a little more carefully, a little higher energy, and there it was. The omega minus particle was his ticket to the Swedish smorgasbord. Okay? Dynamite money. Right? All of these funny things that humans do. Behind the scenes is utter travesty. Okay.
He finally discovered something for himself.
That's right. Yeah. Okay, now let's take a look at the simpler one, the one that doesn't require S6. Just S4 will do for the methane-like molecules. But are there any questions? I just want to make sure everybody has a feeling for what is involved with these tableaus, and is there any question? It's hard to say that you could have a stupid question about this stuff because it is so outlandish. It's just so remarkable. And there's so much yet to be discovered about it, both mathematically and physically. So there is not possible a stupid question about this stuff. Anyway, this is a particular example of a tetrahedral splittings for angular momentum 7. We didn't go that far when we were doing our splittings. We did angular momentum 1. The vector didn't split under octahedral or tetrahedral. We then went to angular momentum 2, and angular momentum 2 managed to split into a doublet. I'm using my hands here, and a triplet. Okay, the triplet was the T2, 2 for angular momentum 2, right? And then there was the E. Depending on the geometry and the charge, E could be up or it could be down. Those are the main splittings, the 3-5 compounds that are responsible for basically all the machines that we're using here, all the semiconductors, everything, all the diodes, all that crap uses 3-5 stuff, and it's splitting like this. So that's a pretty important splitting. But here we are at 7. Okay, we went to 3 just to show a splitting that atomic physicists at the bottom of the periodic chart, the lanthanum line and the actinides line. Okay, there's a lot of F-shell atoms down there, and the F-shell is angular momentum 3, which has 7 states, right? So there's where you would be using U7 to characterize things. But this is angular momentum 7. Okay, so we're talking about 2 times 7 plus 1 is 15 substates here. And here we're splitting them as they would split in a tetrahedral, which is very similar to the way they split in an octahedral crystal or field that had a multipolarity that would be, let's just say, fourfold, that is a quartic, the j to the 4th x, y, and z. So this is not big enough angular momentum to really show a clustering, but they are coming out in the order that the clustering gives. And over here, we're looking at something that has angular momentum 30, as we're used to, now that we have the rotational energy surface and all that stuff. And we're used to having 1, 2, 3, 4, 5, 6 clusters of these irreducible representations that represent the old-fashioned notation of A, T or F, and E, and the T or F come in two flavors. One, that's the vector. Two, that's the tensor. And then there's a scalar A1 and a pseudoscalar A2 showing up in the clusters, which I'll show pictures of again just to remind you in a little bit here. And then there's a big mess down at the other side where you have two clusters that's associated with trigonal symmetry. And the degeneracy down here, if you add up the orbital degeneracy of 1 plus 3 plus 3 plus 1 is 8. That corresponds to the 8 valleys that sit around on the face of an octahedron. And these guys have a degeneracy of orbital numbers of 1 plus 3 plus 2, that's 6. So these are the guys that make up the 6 mountains, of the 6 high points of a rotational energy surface congruent with SF6. But
We just cut out the bad.
okay, after a battery break, the key thing here is to figure out how actually high these spectral lines would be, and I'll show sketches of that in the next slide. In fact, we might go ahead and move the other projector here ahead to show that. This is showing something that I invented that I was very happy about, but no one seemed to want to use it for a long time until they started taking this kind of spectrum. And that is the row vibronic spectral nomogram, where you plot the initial states versus the final states. And everywhere you have an intersection that is active, you draw a 45-degree line and actually will show you the spectrum. What way will it look when it comes out if somebody can scan in the frequency range that has the transitions that we're talking about here. I'll come back to that in just a minute. But right now, the idea is to figure out for methane, which is a Fermi molecule, that's a molecule that has H spin a half, so it's all fermion statistics, all anti-symmetric. And what will happen then, if the spins are all anti-symmetric, then the orbit will be symmetric. So you'll see that when it comes time to do tableaus that are horizontal, that is the conjugate that goes with the tableau of the orbit. This is the tableau of the orbit right here. This would be the shape of the tableau of the spins. Here we're talking about angular momentum 2. I mean, basically that's what it's going to look like. But the hook length formula tells you that for sure. So this will be intensity 5 compared to this poor old fellow, the E, who intensity 1. So 5 to 1 in heights of the spectrum that comes out from that. And if you go over here, you can see the E's. This E right here, sometimes it's barely visible in an actual spectrum. The other two, F2 and F1, they're not quite as high, but they get 3 here. And this one also the same. So that is this formula right here, just giving it directly, something you can use. Now, if you had built the molecule entirely out of deuterium instead of hydrogen, in other words, the isotope they call D, deuterium, D4, CD4, deuterated methane, fully deuterated. You deuterate all 4 of them, or else it's a broken symmetry thing, which is also interesting, not as clean as this. Well, it's just the opposite now. You can't even make the A2, because now the tableaus have to be the same. this thing has to be a vertical tableau to match this, in order to make it mostly symmetric. And this horizontal one has to be matched by a horizontal one. That's a huge spin weight right there. And that's because it's spin 1 for deuterium. And then 6 for this guy. This really gets a peak. And these are more or less the same. F1 and F2 don't care whether they're Fermis or Bose, they're sort of caught in the middle. So that's the thing that I'd like to just let you see, that this kind of elegant formulation is ready for use, certainly for a molecule like this, but it's aimed at much more complicated ones. And the buckyball is one of our targets. So that I think is important, and here is the program. The other thing that comes out of this is that the tableau describe the arrangement of the core electronic spin. We might call it the soul. I sometimes, like to be prosaic about this stuff and anthropomorphize it somewhat. But the idea is that this particular little shape here is not influenced by the transition from this particular ground state to a vibrational excited state of one more quanta vibration. It doesn't care. None of these levels here can talk to any of the ones in the other things. So this one right here, which has for methane associated with the most nuclear spin, and actually this one right here is the one that's associated with the very most. This one has a weight of 5 from that calculation that involves the A2 right there. Okay, so these are the big boys, you might say, but they're not going to talk to any of these or any of these. This is something that you see at low angular momentum. The hyperfine total is maintained. It doesn't give a darn about what's going on outside with the vibrations or even electronic transitions. Way up here, they're going to just stay in this column. So this is called orthomethane. Ortho because the spin states are orthodox. Orthodox meaning more of. I'm being rough here with my etymology. Okay, but it's a good mnemonic in any case. This is ortho. Okay, and then the other stuff is para. The other extreme, pretty much, probably is this one, and this one's sort of meta. So if you're going to use the old Greek names for methane, it would be ortho, and then para, and then meta methane. They're like different chemicals. That's the thing that's really subtle about this. Is they should be in different bottles, and you'll come back in a week and they'll still be in the same, whatever it is, A2 or E or F, because there's no magnetic stuff around. You have some iron in there, you're going to start converting, but very slowly. Just like H2 converts from orthohydrogen to parahydrogen and causes Zeppelin hangars to blow up. That's the little tale I think I've already told you. Okay, so this is all stuff that I find really exciting and very powerful. But here's what we need, you see, to be able to do, and this is where it gets really squirrely, is the larger molecules, buckyball, SF6, adamantane. There are a bunch of molecules with really high symmetry, really high for buckyball, that require the same sort of analysis. And that's where it is really helpful to have this character formula. So here's a formula for just calculating. This is an S6 character calculation going on in about 3 steps. I get that this particular character is 1. The others are -1. Then there's a 2 or 3. There's a lot of characters to S6. But this is just one particular example of a calculation. And these are the definitions of this deterministic expression. This is like a determinant. And you take these funny kind of partial derivatives that have these rules. The partial means you just subtract m, if it's partial m, from each of them and add them up. that's kind of neat. So these are the tableau mu's, those what cycle, but we're talking tableaus now. Mu1 is the length of the first row, mu2 second row, and so forth. So usually these are pretty small. This one only had, this particular tableau here only had 2 rows. And that's what you get when you spin a half. Okay, so that's one thing. The other thing is that the octahedral molecule already has a higher symmetry that is kind of hidden. That is, the permutation symmetry of 6 things is there. But the trouble is, or I should say the blessing is, depending on how much you like SF6, SF6 is very stable. So it is very improbable that I would have a permutation in S6 which would do this. And of course it doesn't want to go, the classical thing. But the idea that I would actually switch nuclei has a probability of cycles per life of the universe. I mean, it's really solid. It's an exponential tunneling rate that has a large negative exponent. And so the probability that this SF6, you know, in the ground state would do that, or any of the permutations of the 720 permutations of the group S6, which is so much larger, 720 compared to this guy right here, which is 48 if I count the inversions. And inversion is also an undoable operation for this thing, to have all of these nuclei switch sides. Not going to happen. But that doesn't mean we shouldn't consider it, because when this molecule forms and the actual core that's made out of the spins will trade. I can have a spin up here, and it's very highly probable under certain conditions that that spin up here would translate, that they switch spins. This one would be up and that one down, say, they'd switch. That's a permutation that can happen with the spins. So the idea that everything is rigidly classical and stuck in a tinker toy molecule, that doesn't go. That's not true. And this stuff really shows that. So what we need to do is we need to do the same kind of correlation between the little octahedral group, very little octahedral group that only has 10 representations, and all of them in general representations of the S6. So S6 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 representations, 11 tableaus, and those have to be correlated with, now the octahedron gets to sit on top of the table. Remember the correlation table that we did, where the octahedral symmetry sits on the side with A1, A2, E, T1, T2, and then some subgroup like C4 or C5 describes the clusters, the induced representations that go with this collapse that we see at high J. Okay, this is going a step further now. Now the little group, the small group, is sitting on top. And this monster, the 720 6 factorial sized group, is now ruling the roost at the core of this molecule. Now with methane, this is not a problem so much, because the methane molecule's core is described by the same one that describes its symmetry outside. If I could just quickly go back to that, just to point out for sure that this guy right here has S4 symmetry both geometrically, and very happy about it, and also with respect to its nuclear spins. So you can use tableaus for both of those and be pretty sure you're describing everything that happens. Not so with SF6. So what you get is this incredible correlation table, okay, and this is it blown up. There is a reference to this one there. But if the fluorines only have spin a half, they cannot make a tableau with more than 2 rows. That is, the Fermi nuclei can have these tableaus to go with them, okay, but only, this is the spin tableau, for total nuclear spin of 3. All spins could possibly be aligned up if they were in that particular one. And then this one has a total angular momentum, spin angular momentum of 2. This is nuclear spin angular momentum we're talking about here. This is 3, this is 2, that's 1, a half plus a half, and then there is, of course, the scalar nuclear spin. These are forbidden. They cannot do it with just spin a half. Now go and get me a bromine or something like that to put there has spin 1. I can start using things that have 3 rows, like that one. That's too much though for that. So these will be allowed, so will these. And the tableau formula tells you how much. It tells you how many you have. And that's why it's, you know, something we can manage pretty well with the powerful mathematics that this permutation stuff gives us. So let's just finish here with a question that we really want to get to, and that is, how does level clustering affect that hyperfine stuff that might be much more limited in its ability to do things to the molecule if it weren't for the level clustering? So the hexafluoride is a pretty good one to look at for this. So I've got his picture down here, just making sure that you see when we talk about S6, we really are talking about S6, and this correlation table is what you deal with. And what I've done here is I've scratched out the orbital states that fermions nuclei, namely this one, would be allowed. They're just allowed this, this, and this because the spins that are going to go with it are going to look like that. So you get to use this one, this one, this one, and this one, okay? But that's crossed out. All of these are crossed out. You can't make a spin to go with this thing, and it has to be opposite. That's what fermions do. It has to use the opposite tableau. The tableau is so elegant for describing the most amazing quantum principle, and that is that you have to have anti-symmetry when you're a fermion with other fermions. But if you're a boson, it's just the opposite. Your phase always symmetry, always in design, always hoping you get together to make a big party. The fermions, they, by having anti-symmetric wave functions, they stay away from each other. They're loners. The bosons are the guys at the fraternity house. No, probably not. They're much better behaved. Okay, so that's what we're dealing with here. And it's really quite remarkable because here's the full table for SF6, assuming I have spin a half. And there's a singlet, there's a triplet, there's a quintet, there's a septet. That's possible. That's possible to see in spectra, really good spectra, the kind of spectra that these guys, Christian Bourdet, Chris Solomon, and Oliver Pfister. Now, Oliver's at Virginia right now. Most, half of his crew migrated to the United States, so we're lucky to have them. In any case, remember what we did to correlate the octahedral species with a lower symmetry that occurred spontaneously. That is, the lower symmetry of having the angular momentum get stuck on fourfold axes in states that were described by 0 mod 4, or 1 mod 4, or 2 mod 4 or minus 1 mod 4. There were 4 possibilities to fall onto the fourfold axis, which was the preferred axis for most of them, as you may have seen. So when that happens, for example, with 0 mod 4, you get A1, E1, and T1 all together very close in energy, and that's something we've looked at already. And this is just a picture of the tunneling waves with their A1, T1, and E placement blown up, and these are all things that we've kind of looked at before, maybe not with quite this detail, described by just a 6x6 tunneling Hamiltonian, in which I assume that there's no tunneling across, only tunneling nearest neighbor. If I have that, that determines the spectrum in a 2-to-1 fashion like that. So the question is, when the molecule collapses to the point where the splittings here are so tiny, what happens when you get the resonances of the nuclear spins to work? And this is just a cartoon sketch of my guess of what happens as you bring the E1, T1, and A1 from this collection together with all the the full 6 SX symmetry, now getting to do its thing down here. And then the T1s and T2s, they also get together. And then there's a question of how are they going to get together. There's a hierarchy that gets going. But this is the main deal. This is what's happening. Normally the molecule flying with its wave functions that we've been describing so far has all of these axes, x, y, and z, plus and minus, equivalent. But if it does get a really high angular momentum, it only has to be 20 or 30 before this starts to happen, it starts to say, I'm just going to stay in one position. I'm not going to tunnel anymore. It's so hard to travel. The food's terrible on the airplane. I'm not going to do it. I'm just going to stay on this one axis. Then you've got 4 nuclei that are in a different environment most of the time than these guys that are stuck on the poles where it's really cold. The magnetic field this guy feels is practically nothing. These guys are enjoying a much higher magnetic field, and the spins are saying, oh boy, it's like being in a sauna or something. This is wonderful down here. We like it hot. So that's the thing that's going to happen as these come together. You get entirely different kinds of states that really no one anticipated. We were the first to say this, and stuff we're going to talk about later on. This is just a diagram for the methane-like molecules, okay, where you have the weight 5, the weight 3, and the weight 2 very clearly designated there according to the nuclear spin tableaus. There's a linear combination, and we'll be doing some of that in the next few lectures. So this is a tetrahedral molecule that's stuck, rotating on the fourfold. That's not so interesting because still all 4 nuclei are feeling the same environment. It's when this thing turns to the threefold axis that it goes crazy. This one already has a problem on its preferred axis, the fourfold. And this is all going on for the CF4 down in here. Okay. These clusters are getting jammed together. I used to say they're living in sin and they're paying for it. Okay, so this is SF6, and we're talking about what's going on down in this lower region here, where those spins and the S6 really plays a big role. No question about it, and that has been verified. These experiments have shown that to be the case. And this is the one of the clusters. This is the 2 mod 4 cluster with its hyperfine states coming together, now mixing crazily to make things that are 4 plus 2, 4 plus 2. The tableau's being broken by that happenstance of getting stuck on just one axis. or looking like that's what's happening. So we've got a lot to talk about. We haven't yet, and this is just the last slide here, I think, shown how to get irreducible representations. Now you already know these. This is sine and cosine of 120 degrees, right? Remember I said it was the most complicated derivation of that trigonometry, right? When we actually worked it out using the projection operators. Okay? Well, that happens to be what the tableaus ordered. Using hook links. You use these hook links in this way, and you generate, this is an S5 representation being generated in just a very short period for the permutation 4-5. And that's the thing that this does, is it generates a permutation n minus 1 for each of the SNs. And then it's up to you, and that's the thing we still need to discuss, put them together to make all the others. And so far, there's no hook length formula that goes ahead and does that job for you. But then, most of these problems are going to be done on a computer, so we don't care if the computer has to work pretty hard to multiply all those matrices. That's going to be just a very short job. Okay, I think that's it for today. And we're lucky to have that. All the trash that happened during the Christmas vacation, the computer went crazy. Then the math type went crazy, and then the web went crazy, and you name it. I didn't think there was very much that was crazy. And of course, then every once in a while you look what's going on in Washington, you figure, my stuff isn't so bad.
Yeah, if your computer malfunctions, it's not going to lead to a 60 minutes interview.
Right. And that's a hot interview, but I'm worried about the one that's going to involve the North Koreans.
Oh yeah.
That's a,